Today we're gonna start with chapter 1 section 3, equations and graphs of polynomial functions. In this section we're gonna see how we can get a polynomial function in the factored form, and based on that how we can sketch a graph. Let's say we got a function like this, y equals to x plus 1 times x minus 2 times x plus 3. Based on the factors that we have here, we can find the x-intercepts. We know that for finding the x-intercept, we should put y as 0 and see what x's would give us the y as 0. So if we want to have the product of these three factors to be 0, either the first factor is 0, the second one is 0, or the third one is 0. So what value of x make this x plus 1 0, x being negative 1? For this one, x being positive 2, and for this one, x being negative 3. These are the three x-intercepts that we have. In order to graph this, we can just use these three x-intercepts. Now, before we start doing the graph, there's something called an order for each of the factors that you need to know. So, if we have a function like this, our first factor here doesn't have any special order. The order is just 1, and you can find the order based on the power of that factor. So the exponent for this other factor here, x plus 1, is 2. The x-intercept here corresponding to this factor is negative 1, so we say that we have an x-intercept at x equal to negative 1 with order 2. In this other one we have an x-intercept at negative 3 with an order of, since we have an exponent of 3 here, the order would be 3. Now this is how you can find the order, but we need to know how each of the orders can affect the graph. So if you have an order of 1, let's say at x equal to 2, 1 and 2 here, the graph would just pass that point or that x-intercept when you get close to it. Something like this, if this is point 2. When the order is 2, let's say again at x equal to 2, if we're on this side of the x-axis, when you get to the x-intercept, you're gonna stay on the same side of the x-axis, so the sign of the function doesn't change. You're kinda gonna have an bounce back, so you're gonna hit the x-intercept here, but you would bounce back in the same direction, just like how you have a parabola. And for order 3, again at x equal to 2, you would kinda have the same effect as when you have for function y equals to x cubed. So this time we're gonna pass the x-axis just like the order 1, but the slope of the function would be a little more flat towards the x-axis when you get close to the x-intercept. So something like this. Their slope is gonna get closer and closer, and then you would go down and continue. So for order 1 we would just pass that x-intercept. For order 2 we're not gonna pass that the x-axis, we're gonna bounce back. And for order 3 the slope would get a little flat towards the x-axis and then you would pass that point. Now we're gonna see how we can sketch the graphs or find the equations in the following examples. So we're gonna do example number 1 on page 33. So we need to, for each of the graphs that we have, we need to find the least possible degree and the sign of the leading coefficient, the x-intercept and the factors of the function, the intervals where the function is positive and the intervals where the function is negative. So if you go to page 33 in part 8, in the graph that we have, you can see that we have 3 x-intercepts, and based on the look of it we can say that all of the x-intercepts have an order of 1. So the degree of this function, so for part A the degree would be 3. Since we have 3 x-intercepts and each of them has an order of 1. And as you can see, the graph goes from quadrant 2 to quadrant 4. So we can say that the leading coefficient has a negative sign. Now the x-intercepts are at, so the x-intercepts are at, the first one that we can see is at -5. We have another one at 0, and the third one is at 3. Now, the intervals where the function is positive and the intervals where the function is negative, as you can see on the graph, anywhere where we're above the x-axis, you can say that in those intervals the function is positive, and whenever we're under the x-axis or below the x-axis, we can say that the function is negative. So we're starting in quadrant 2, so from negative infinity all the way to our first x-intercept at -5, the function is positive. Then from -5 to our second x-intercept, which is at 0, we're below the x-axis, so the function is negative. Then we go back above the x-axis between 0 and 3, so again we're in the positive side. And after 3 we go back down all the way to positive infinity, so this is going to be negative. So this is for part A. For part B, here you can see that we have 3 x-intercepts. However, the last one or the third one, which is at points x equal to 3, you can see that the graph has an behavior similar to order 2. So although there are 3 x-intercepts, one of them has an order of 2, so we would know that the degree of this one would be 4. So 1 plus 1, and the last one has an order of 2's, so 1 plus 1 plus 2, and that's 4. The function goes from quadrant 2 to quadrant 1, so the leading coefficient is positive. The x-intercepts are at the first one is at -2, the next one is at 1, and the last one is at 3. The intervals where the function is positive and where it's negative, from negative infinity to our first x-intercept, which is -2, the function is positive. From -2 to 1, it's negative. 1, 2, 3, again positive. From 3 to infinity, also positive. Because we bounced back and continued on the same side of the x-axis, and the order here was 2. Now if you also want to write the factors for part A and B, we have a -5 here, so the factor is going to be x plus 5. We have a 0, so the factor is just an x, so I'm going to put it at the beginning. And for the 3 that we have, it's going to be x minus 3. Now for the part B, we have -2, so if we're going to have x plus 2 as the factor, we have 1, so it's x minus 1, and we have 3, which is x minus 3. But as you can see, there's an order of 2 here, so you're going to put a power of 2, or this factor would be squared. Alright, so next we're gonna do example number 2, page 34. Sketch a graph of each polynomial function. So in this example, we have the equations and we wanna sketch the graph. So let's start with the first one, part A. The equation is y equal to x minus 1 times x plus 2 times x plus 3. So in order to sketch the graph, first we're gonna find the degree of this function. We have an x here, another one here, and a third one here, so the degree is 3. Let me write this down here. So the degree is 3. Then we're gonna see what's the leading coefficient. So since there is no coefficient behind any of the x's here or all the way at the beginning, so it's just gonna be a positive value, and it's going to be 1. Now, based on the degree and the leading coefficient, we can find the end behavior. So, since the degree is an odd number, and the leading coefficient is positive, we're gonna go from quadrant 3 to quadrant 1. Next, we're gonna find the x-intercepts. We have the first one at 1, we have another one at -2, and another one at -3. So 1, -2, and -3 are the x-intercepts. We're also gonna find the y-intercept. In order to find the y-intercept, you need to put x as 0 and see what value you're gonna get for y. So y equals to -1. I'm getting -1 by putting 0 here, times, if you put 0 here, you're gonna get 2. If you put 0 in the last one, you're gonna get 3. -1 times 2 times 3 is going to be -6, and that's your y-intercept. Now let's see how we can sketch a graph. So let's find the x-intercepts. We have one at 1 here. We have one at -2 here, and another one at -3, so here. Our end behavior is from quadrant 3 to quadrant 1, so we know that we're gonna start here and finish up here. So I'm gonna start from somewhere around here and go to my first x-intercept. So I go here all the way to my first x-intercept, but since the order of this one is just 1, I would pass it. Now I have to go back to my second x-intercept, so I would come back down. Our y-intercept is at -6, so 1, 2, 3, 4, continue this line, 5, 6, so I have to go all the way here to -6, and then we would come back up to the next intercept, which also has an order of 1, so you just pass that point, and as we were supposed to, we finished up in quadrant 1, so from 3 to 1, and we had hit all the x-intercepts and the y-intercept here. Alright, so for part B, the equation that we have is -2 times x minus 1 squared times x plus 2. The degree here is going to be 3 because we have x to the power of 2 here and another x here. The leading coefficient is this number here, -2. So -2, which is a negative number. Now having an odd degree with a negative leading coefficient would result of having a end behavior of quadrant 2 to quadrant 4. The x-intercepts are this one. This factor here would give us an x-intercept at 1 with order 2. And the next one is here at negative 2. The y-intercept would be putting 0 instead of the x's, negative 2 times, if you put a 0 here, 0 minus 1 is negative 1, but when you take it to the power of 2, it's just 1. And if you put 0 here, you're gonna get 2. So the y-intercept is at negative 4. So we have an x-intercept at negative 2 here, and the next one is at 1. Gonna start in quadrant 2 and finish up in quadrant 4. So I'm gonna start here, and our y-intercept is negative 4. So I'm gonna start here, go all the way down, and then you would come back and hit your, sorry about that, y-intercept. Then you would continue going up all the way to your next x-intercept, but we need to know that at x-intercept at 1, the order is 2, so you're just gonna hit the x-intercept and bounce back and continue on the same side of the x-axis. And as we were supposed to, we started in quadrant 2 and finished up in quadrant 4. And for part C, we have y equals to negative 2x plus 1 to the power of 3 this time, times x minus 3. So we have x to the power of 3 here times another x, so the degree is 4. Leading coefficient would be the product of the coefficients of the x. We have a negative here at the beginning, and we have a 2 here and a 1. This 2, when it goes to the power of 3, would become an 8. And there's a negative sign here, so the leading coefficient is negative 8. Having an even degree function with a negative leading coefficient, we get an end behavior from quadrant 3 to quadrant 4. The x-intercepts are, if you put negative 1 over 2 here, this factor would be 0, so you have 1 at negative 1 over 2, order 3, and the next one is at 3. For finding the y-intercept, you're going to put 0 instead of the x's. Negative 1 to the power of 3 times negative 3. So the y-intercept is at 3. So we have 1 at negative 1 over 2, which is here. And the next one is at 3, so these are our two x-intercepts. I'm gonna start in 3 and finish up in 4. And the y-intercept is at 3. 1, 2, 3, so here. Since there's an order of 3 next to this x-intercept, I'm gonna start in quadrant 3. When I get closer to my x-intercept, I'm gonna get a little flat towards the x-axis and then continue. So something like this. You would go up and then we would come back to our next x-intercept, but since there is no order or an order of 1, you would just pass that point and we finish in quadrant 4 just how we were supposed to. The next thing that we're gonna work on is we want to see what's the difference between even function and an odd function. So you have the definition for each of them on page 36 and 37. So the bottom of the page 36, you can see that an even degree polynomial function is going to be an even function if the exponent of each term of the equation is even. An even function satisfies the property f of negative x equals to f of x, and an even function is symmetric about the y-axis. So for an even function, first of all, we know that it has to be even degree. So the degree is even. Now there are three main things that we're gonna see here. The first one would be the exponent of each term is even. The second one would be satisfying the property of f of negative x being equal to f of x. And the third one is symmetry about the x-axis. I'm sorry, about the y-axis. And we can say that this is a line symmetry. Now, this was for even. So the differences between even and odd would be the exponent of each term for an odd function is odd. This time f of negative x is going to be equal to negative f of x. And we have a symmetry about the origin, which is a point, so we have point symmetry. So I want you to work on the third example of this part on page. So page 30.